Hi, welcome to another video on control systems. Again, in this video, we will be looking at the continuation of the Routh's stability criterion. These are the prerequisites. Okay, with these prerequisites, if we again, okay, in the previous video, we are talking about the second case of Routh's array, where the first element of a particular row becomes 0 and other elements are non-zero. How do we complete the Routh's array? So in the third case of Routh's array, assume that this is the Routh's array. We have so assume that this is S per 5, S per 4, S3, and then S2, S1. You have so many elements of the Routh's array. Assume that you have something like this. Assume that a particular row becomes all 0 0 upon writing the elements of so and so. Assume that this s power 1 row becomes 0 0 0. So when it is 0 0 0, you cannot continue the subsequent elements because this will become infinity, infinity, infinity. Then you cannot do this. So whenever in this case 3, all elements of a row becoming 0. When it is something like all 0 0 0, you cannot continue the array. So in such case, we have to consider an auxiliary equation. So what is this auxiliary equation? So this is an auxiliary equation. We call it as A of S. Assume that a row above this is something like this. It is a 3 4 0. Assume that it is 3 4 0. So what is this 340 actually corresponds to? This actually corresponds to 3s square plus 4 equal to 0 is my equation, a row above this. So then I'll call this as the auxiliary equation. So now, so when you consider an auxiliary equation, an auxiliary equation is considered when forming a Routh's array. If complete row becomes 0 0 0, then you take a row above that zeroth row and write the auxiliary equation. If it is 3, assume that it is 3 4 0, then the auxiliary equation, because we know that it is alternate powers, so these are the coefficients of alternate powers of s here. Since it is s square row, it is s square, the alternate power of s square is, you have to leave out s, and it is s power 0, which is 1 there. So you have this as the auxiliary equation. If this is the auxiliary equation, then how do we continue this? So I need to eliminate this 0 0 0. Then what are the values of these things? So what I do is I will differentiate this auxiliary equation with respect to s and write this is now 6s equal to 0. So now you have a differentiated auxiliary equation. You have 6s as the term. So then this will become 6. Now you have to eliminate this 0 0 0. You have to replace it by 6 0 0. Then you have to complete the. Then you can continue there, because this will never be. This is no more infinity. Now this will become 4 0 0. So you'll be completing the Routh's array in spite of having it as 0 0 0. You did eliminate 0 0 0 by taking the auxiliary equation and its derivative. The derivative coefficient of this is written as the modified row elements of this particular row. So then you comment on what is the sign changes. If there are no sign changes, then you say all are there to the left hand side. If there is one sign change, you say one to the right hand side. If there are two sign changes, then you say two roots onto the right hand side of the S plane. So that's what is the third case. So we have three different cases of Routh's array. The first case, just completion without any issues. If there are no sign change, all no none of the closed loop goes to the right hand side. If there are two sign changes, then two roots onto the right hand side. There is one sign change, it's again one closed loop pole to the right hand side. In second case, we found that if there is a row becoming if one element of a row is becoming 0, then you say it as, so that's your second case, where you have only the first element is becoming 0. Where is that? Right, that is okay. Okay, this is my second case where only the first element is 0. It's something blah 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 blah, blah. It is 0 3 2 something like this. And this is 0, then you have to replace the entire characteristic equation by 1 over z, reframe the characteristic equation, then proceed, rewrite the other, and then get the result obtained. And in the third case, we know that you're supposed to suppose you have all elements of a particular row become 0, then write the auxiliary equation, which is nothing but a row above that. Then you complete this by taking the derivative, and then find out the number of sign changes. Okay, now let us take specific examples and then try to use these concepts of number of sign changes and comment on the stability of the system. So for which I have the problems already solved. Now we can just have a look at this. Characteristic equation is already given here. So this is a characteristic equation: s power 4 2s square plus 8s square plus 4s plus 3. You can see I'm writing the coefficients of s power 4 is 1, s square is 8, and s power 0 is 3. And then here this is 2 and this is 4, and you don't have any further element, it is now 0. So now these are the first two rows of the Routh array, which will be directly obtained from the characteristic equation. Then the subsequent rows or subsequent elements of the row are obtained using the equation what we discussed in the previous video, or it is as per this. Let me just show you that it is as per this equation. So this is as per this equation. You're writing B1, B2, B3, and then C1, C2, C3s, and D1, D2, D3s are written as per the cross multiplication and division by the first element of the particular row. So that's what is there here. Of course, you can certainly find out this becomes a 630. That's what is 630 here, and then upon doing the subsequent one, then this becomes 300, and then last finally it becomes again 300. So this is what the ultimate Routh array looks like upon rewriting them in the simplest form. So if you can see, it is positive, 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 no sign chain in the first column of the Routh array, meaning that no closed loop pole to the right hand side of the S-plane, meaning that all the poles are there on the left hand side of the S-plane. So naturally we say system is stable because all the closed loop poles are on the left hand side of the S-plane. One disadvantage with this Routh array is you will not get the exact location of the closed loop poles, but you certainly get the region of existence. When I say region, whether it is there on right hand side or left hand side, you'll get to know. So since there are no sign change, means all of them are on the left hand side of the S-plane, so system is stable. Now let us see the second one. This is the second one. If you can see here, this is your characteristic equation. So it's a sixth order system. I'm writing the Routh array. The first two rows are written from the characteristic equation as it is. See here, it is 1 2 5 20, which is nothing but 1 2 5 20. The coefficients of s power 6, s power 4, s square, and s power 0, and this is coefficient of s power 5, s cube, and s, and then you don't have s power minus 1, that's why it is 0 here. Then the subsequent rows, which is nothing but 3 into 6 minus 1 into 9 by 3. Then it is 3 into 5 minus 1 into 12 by 3. It is this. Likewise, you are doing. Of course, only you have to do it once and then get the hold on. Okay, how do I write the Routh array? This is the Routh array completed. So once Routh array is completed, you can see this is the completed Routh array. So if we can see here, of course I'm just rewriting that. So I'm just rewriting the same thing over here. It's a simplified version. If we can see here, this is 1 3, you can see, just see the sign changes. It is plus, plus, minus, then plus. If you basically see, the number of sign changes are happening twice. Plus to plus, no sign change. Plus to minus 1, minus to plus another 1. There are two sign changes. So two closed loop poles are onto the right hand side of the plane. So system is unstable. So this is the case one of your Routh array, where you're trying to find how many are there to the left and right, uh, depending on the number of sign changes. So you have comfortably completed both the Routh arrays without any difficulties by just using those equations of B1, C1, D1, all those stuff. Let us move on. Again, I just recommend you to write this Routh array. You have to write all these elements from those equations, and then get the whole done writing the Routh array. So once you are done with the Routh array, then it is commenting on the system stability. Okay, now let us see what is this. Okay, let us take this third one. So it is now s power 5 plus s power 4 plus 2s cube plus 2s square plus 3s plus 5. Now I am writing the Routh array. Upon writing the Routh array, you had this. Sorry, uh, just a minute. This is the Routh array. See, now upon writing that, here you had the first element as 0, the second element is minus 2, the third element is again 0, but the first element is 0. This is a non-zero. When one of the element is non-zero, you cannot continue the array, because this will become infinity infinity. You cannot continue. So as infinity comes in a row, it's not possible to continue. As not all elements of the row are not 0. Again, not all the elements are 0. Then you have to replace s by 1 by z. So here this s is there, no? You replace it by 1 by z. So upon replacing it by 1 by z, you have this. See here, you have this term. Let me just rewrite it. So you have this. This is coming from this particular equation. I'm replacing z by, or s by 1 by z. See here, this is 1 by z power 5, then this is 1 by z power 4, then it is 2 by z cube, then it is 2 by z square, 3 by z, and 5. So now you simplify this by taking LCM. Upon taking LCM, the LCM becomes z power 5. Of course, you can see this entire equation, then this will become 5z5, 5z to the power of 5, 3z to the power of 4, 2z cube, 2z square, then it is z, then it is 1. So this is what is, upon taking LCM, you rewrite the characteristic equation by this way. That's what is written here. This is further written like this. Now you have a new characteristic equation by replacing s by 1 over z. So now you rewrite the Routh array. You can see now on the same lines, it is 5, 2, 1, then 3 to 1. You are trying to complete the Routh array. You are completing the Routh array by using the equations. You found that the completed Routh array of this modified characteristic equation is something like this. So it has got again two sign changes. See here, it has got some plus to minus, then minus to plus. So there are two sign changes, means two closed loop poles are there onto the right hand side of this plane. So system is unstable. System is unstable. That's how, suppose if the one of the first element becomes 0, then you have to replace s by 1 by z. So that was our second case, where we just try to replace this. So if I just go back to our second case, this is how we got. So this was 0 from AB. Actually what we had was 0, minus 2, and 0. Since it is 0, then you have to replace s by 1 by z, and then rewrite the characteristic equation, then reform the Routh's array. Then finally you comment on the number of closed loop poles to the right hand side of the display. That's what is this. And let us move on. Upon moving on to the fourth one, you can see this is the fourth characteristic equation. You have this Routh's array. So we are writing the first two elements. You can see it's also possible to just reduce this, okay, elements. So if it is all elements are divisible by a certain number, you can divide. Instead of having it as 4 8 4, you can write it as, divide the entire row by 4, you can write it as 1 to 1. I can change the elements from 4 8 1 4 8 4 to 1 to 1, because it doesn't matter whether you have it as 4 8 4 or 1 to 1, because all the elements of that row is divided by same number. So then you complete the Routh's array. Let us see what happens. Okay, now you are completing the Routh's array and then trying to find out. Let me just see what is this. Is that completed Routh's array? You can see you have, this is the finally how it looks. Again, you can find there are two sign changes happening here, plus to minus and then minus to plus, meaning that system has two roots onto the right hand side of the plane. So system is unstable. Okay, let us see now what happens. We are completing the row now. You can see now we have 0 minus 32 0. Then it's again first element is 0, you have to replace s by 1 over z, then you are rewriting the equation. You had this. Now when you have something like this, this is minus 32 z power 4, so on, so then you just multiply everything with minus, then you just reform the characteristic equation, write the Routh's array, and then find what's happening. You can see, interestingly, all the elements of this row is becoming 0 0 0. So you have case 2, case 3 coming in the same problem. It's interesting. See, now this is 0 0 0. When it is 0 0 0, so what you have to do, this is 0 0 0, then you have to take the auxiliary equation. You can see, as z power 1 row all elements are 0, then it's impossible to continue the Routh's array. What you have to do, you have to take the auxiliary equation. Auxiliary equation is this actually. So you can see it is 4z square, 4, of course I written it as s square, or in z square, 4z square minus 1, and then you are differentiating that with respect to, of course you can make it as with respect to z or s. Now it is 8s. You can see now you are replacing this 0 0 0 by 8 0 0. Then you are completing the Routh's array, and then you found that there is one, this is negative sign. So ultimately what's happening, this is what you are ending with. See here, this is your completed Routh's array upon replacing s by 1 over z, and then completing the Routh's array by taking the auxiliary equation and its derivative, all those stuff. You end up with something like this, meaning plus to plus, plus to minus, again plus to plus, sorry, plus to plus, all of them are plus to plus, plus to plus, finally it is plus to minus, meaning that there are one sign change. So there are one sign change happening here, meaning that there is there is one closed loop pole to the right hand side of the screen, one closed loop pole to the right hand side of the screen. Then what does this auxiliary equation actually mean here? The auxiliary equation mean here is, so it's a part of that overall equation. It's a part of that overall equation. We can actually find the roots of that also. We can actually find the roots of that also. Okay, let us go to next problem. It's a seventh order system. You are writing again the Routh's array, completing that Routh's array by using that equations. Let me see how it looks like. This is finally how it looks. Great. So now this is having, again, two sign change. Plus 2 minus, one negative sign means in the middle means it will going to have two sign changes, plus to minus and then minus to plus, meaning that there are two uh, poles to the right hand side of the S-plane. So that's why the system is unstable. That's why the system is unstable in this problem. In this problem, there are two sign changes. Let us move on and then try to find out what is this. Okay, now you are actually asked to find the closed loop poles. It's not exactly the location. They are actually asking you to find the closed loop poles. So let us see how do we do that. Just write the Routh array. You can see there we are writing the Routh array. So upon writing the Routh array, it is interesting to see you have a 0, 0, 0 element coming. Whenever you have a 0, 0, 0 element, you have to take the auxiliary equation. Auxiliary equation is this: you have 2, 18 and 0 as the elements. So then this auxiliary equation will become 2s square plus 18. So we know that it's a alternate powers of these are the coefficients of alternate powers of s. Here it is of s square, and this is of s power 0. So that's why it is 2s square plus 18 equal to 0. Then you take the derivative of this, so which happens to be okay, sorry, this is actually uh, 4s. So that is one mistake. So this will be 4s. So since it is 4s, then this will become 4. This is not 4s, but this is actually 4s. Okay, upon doing that, what do you have? Just let me just go back to that. See here, this is your completed Routh array. So let me just tell you how do you find that roots. Let me just rewrite that over here and then let us dwell on this. So I have a equation. Let me not too much bother about the equation. What is there? So I have an auxiliary equation which is nothing but 2s square plus 18. I have a del of s which is nothing but s power 4 plus 2s cube plus 11s square plus 18s plus 18. Let me just dwell on this. Fine. This is what your auxiliary equation. This is what is our auxiliary, sorry, characteristic equation. Actually, what is this auxiliary equation is this del of s, the overall characteristic equation of a system has auxiliary equation as a part of it, and because this is overall order is 4, this order is 2, then I should have one more part of this, my second auxiliary equation of my characteristic equation. So this I know. What is this? This is s square plus 18. How do I know this? I can know this. I can know what is B of s if I divide del of s by A of s. Del of s by A of s will give me what is the second part of my auxiliary equation of my characteristic equation. So that's what is there here. See here? So now that part, that B of s is actually how much? 0.5 s square plus s plus 1. How did you get this 0.5 s square plus s plus 1? It's actually dividing the characteristic equation by the auxiliary equation. Can you see here? This is my characteristic equation divided by the auxiliary equation. Are you not getting this B of s? So now what I'm trying to do is, so you have a characteristic equation, you have the auxiliary equation, divide this characteristic equation by auxiliary equation, I'll get the other equation corresponding to the characteristic equation, which is the second part of my characteristic equation. So I know what is this. Of course, we know what is E of s, which is nothing but s square plus 18, and we can find this. So this is B of s, this is A of s. So now you can see there are two roots of this, there are two roots of this. So overall there are four roots of this characteristic equation. Then we know what are the roots of this. So s square is nothing but minus 18, then s is nothing but plus or minus j root of 18. So that happens to be my two roots of this, and then you have to find the roots of this, so which you can easily find it using the calculator. So that's what is there here. Can you see it? The other two roots, okay, is actually 2s square. Is it 2s square? Let me just go back here and then find, sorry, let me just go back here. What is this? This is actually, this is 2s square. This is 2s square plus 18, then this is 2s, and this is 2s, then this is 2, then this is by 2. So it is root of 18 by 2, it's actually 9 means, okay, 3. Plus or minus j root, plus or minus j3 is the roots of this. Then you find what are the roots of this. It's actually, you can find it here. See? So now, what are the 4 roots you have? The 4 roots you have is plus or minus j3, minus 1 plus j1, and minus 1 minus j1. So these are the 4 roots of this particular equation, because you are asked to find the closed loop poles. One is plus j3, other is minus j3, other is minus 1 plus j1, other is minus 1 minus j1. So meaning that you can see all the poles are there onto the left hand side of the line, but 2 are on the imagined axis. 2 are there on the imagined axis. That's what is you can find here. Can you see any sign change? No sign change. No sign change means no pole to the right hand side of the plane, which is true also here. Are there any poles to the right hand side of this plane? So all real parts are negative. So no poles, no poles on right hand side. No poles on right hand side. But are they all on left hand side? I can't guarantee, because it's not true, because you have two poles on the imagined axis. One is at plus j3, other is at minus j3. So what does first come the root surface is how many are there onto the right hand side of the plane. If there are no sign change, then no poles to the right hand side. How about the poles? The poles are now as per this. 2 are on the left hand side and 2 are on the imagined axis, because you ended with an auxiliary equation. An auxiliary equation may yield poles on the imagined axis. Of course, auxiliary equation means you're going to have poles on the imaginary axis of the system, of the S-plane. I hope you are getting that concept. Here you can see there are no sign changes. If there are no sign changes, let us say there are no closed loop poles onto the right hand side. That's it. Where are the poles? If you actually find the pole position, then you can see there are two poles on the imagined axis. There are two poles on the left hand side of the S-plane. So system is now oscillatory with a frequency of 3 radian per second. Okay, let us move on. Let us move on to this. See, sorry. Uh, just a minute. Let us go here. Let me slightly minimize this. Again, I recommend you to write this once. Without writing, just seeing the video is of no use. You have to spend quality time in writing the equation, and writing the Routh array, getting these things. Can you see now? This row is becoming 0, 0, 0. When this is 0, 0, 0, you end up with the auxiliary equation and its derivative. Once you get the derivative, continue the Routh array. Can you see? I'm just continuing the Routh array by taking the derivative of the auxiliary equation. I have continued that, and then obtained what are final. See you now. I got this as my auxiliary equation. This is my overall characteristic equation. Trying to find what is my BFS, that is the second part of my auxiliary equation, or second auxiliary equation. And upon finding, I found that the poles are one onto the left hand side, one onto the right hand side, and two are on the imagined axis. Two are on the imagined axis. So now, how many poles do we have now? We actually have, this is fourth order, this is fifth order. So you have in this fourth order system you have these as your poles. If you can see here, the roots of this fifth order are, one is at here, one is at on the right hand side, one is on the left hand side, plus or minus j5, and this is also on the left hand side. You have typically the equation is s minus 1, s plus 1, s plus or minus j5, s plus 2. So you have one pole to the right hand side of the plane, which is clearly evident in your roots array also, because in roots array you ended with one sign change. Can you see there is one sign change? I think that is written at the last. See here, is it not there one sign change? So if you can see the final roots array, it is positive sign, positive sign, positive sign, positive sign, positive sign, and there is a negative sign at the last, meaning that one sign change means one pole to the right hand side of this plane. How about the exact location? Because we completed this roots array by taking the auxiliary equation. So we actually know the auxiliary equation. We know the second auxiliary equation also. Then we could know the exact pole position, and exact pole positions confirm that there is one pole to the right hand side of the plane, and two are onto the left hand side, and two are on the imaginary axis. So that's what is the conclusion of this particular problem. So this is a very interesting problem. I recommend you to understand it to the core and then proceed. Let us see the next problem. If you can see here also, I'm having a auxiliary equation. You can see it is 0 0 0 upon writing the roots array. Then you write the auxiliary equation, which is nothing but, again, if you can see here, we are reducing this elements of the roots array, which is 3 9 6 is there. I'm replacing it by 1 3 2, and you have 2 6 4, you replace it by 1 3 2. So when you do that, you can see it's becoming 0 0 0. When it is 0 0 0, it's what a condition, which is our third case, where you have the entire elements are 0. Then you have to take the auxiliary equation, then continue this by taking the uh, derivative of the auxiliary equation. It is this. Then complete the roots array, and then what we are trying to do here is we are trying to obtain the second auxiliary equation, which we set it as b of s. You can see this is a of s, this is upon division, this is b of s. This is actually give you what are the exact position of the poles. That's what you have here. So these are the pole positions. You can see these are the poles: minus 1, minus 2, plus or minus j1, plus or minus j root 2. If you actually find the roots of this, or the, if you can read the first column of your roots array, I think you will end up with one. What is the first column of your roots array? So your roots array is actually giving uh, all the poles, because there are no sign change of first column of the roots array. When there is no sign change means actually there are no poles to the right hand side of the plane. But you can see it is minus minus, both are on the left hand side, but the poles are on the imagined axis. You have four poles on the imagined axis, which is at plus or minus j1 and plus or minus j root 2. The system is actually oscillatory. If you can see here, this doesn't have any sign change. No, you can see there are no sign changes, so no closed loop poles on the right hand side. But where the poles are on left hand side and on the image axis, so it's highly recommended. You should write the roots array of all these things. If you are comfortably getting all these things, then nobody can stop you in mastering this roots array and uh, finding the roots of the system. So we'll just dwell on a few more such type of problems in the coming video also.